In this video, we're going to look at some application of vectors that traditionally appear in math classes around this stage. They're useful for getting some insight into how you'd connect real-world movement, velocities, accelerations to the more mathematical notation we've introduced here. Let's start with an example about an airplane that is moving in a direction due east at an airspeed of 600 kilometers per hour. And the idea is that the plane moves relative to the air. And that's totally reasonable. However, the wind is also moving relative to the ground. So the air is moving relative to the ground. And if that's the case, then the actual net motion of the plane relative to the ground is going to be a sum of those two effects. How is the plane moving relative to the air, and how is the air moving relative to the ground? Well, how do we track this down? Well, first we have to define our directions. And so let's call the x direction east and the positive y direction north. And so what we have at first glance is the 600 kilometer an hour due east vector. That is the air, let's call it the plane. And then the additional effect is thrown in for a tailwind of 80 kilometers per hour from the northwest. So north and west. So from the northwest means pushing down in this direction. So we have the wind. And what we're going to do then is put those head to tail. Here's our wind. And what we're interested in computing is this net vector here. That is the net plane with respect to the ground vector. And we are asked specifically what's the velocity vector, so we can return that or compute that using components. All right, let's tackle that now. If we're going to use components anyway, the plane vector, let's just call that P, with a little vector hat. We can use units of kilometers per hour for everything here. So it would be 600 due east with 0 north or south components. So that P vector is a simple all x, 0 y component when we draw that out. The wind is a little more complicated. We've been provided the information in a reasonable way, which is that it's heading southeast, but we need to break it into components before we can use that. So I'm going to draw a slightly larger version down here. The idea is that this length is 80, and we have, let's draw it on the other axis here, we'll have a positive something and positive something for x, and then a negative something for y, negative component for y, and we need to figure out what those ratios are. Well, this triangle is similar to one of our famous 1, 1, root 2 triangles, 45, 45 triangles. Though that's a bit ugly to work with when we have the 80, we can also convert that to a triangle that has 1 on this axis, and then 1 over root 2, and 1 over root 2 for the horizontal and vertical sides. If we note the pattern here, we scale up the hypotenuse by 80, we're going to scale up these sides by 80, and we're going to have 80 over root 2 and 80 over root 2 for those two components. What that does for us is it immediately gives us the wind in component form. It'll be positive 80 over root 2 for the x component, and if y is north, but we're going south, the y component would be negative 80 over root 2. Once we have these component forms, then it's almost trivial to add these up. We literally take the first vector and we add it to the second vector. That will give us this direction plus the effect of the wind and give us the net vector overall. And we could compute values here if we liked. Though we might as well keep everything exact. So we'll have 600 plus 80 over root 2. That is the x component. And then 0 minus 80 over root 2, that's just negative 80 over root 2 as the y component. this would be the net velocity of the plane with respect to the ground. There we are. We're going to look at a similar scenario where again we have an airplane flying at a certain speed and we have a wind that's blowing from the south at 50 kilometers an hour. We're going to change things up a little bit here though by asking in what direction should the plane go so that we end up going due east. So we're going to build our directions the same way we did before, x and y being representing east and north. And with those, we have one of the vectors already. The winds are blowing from the south, that implies to the north. And so we'd have a wind vector, let's call it W this time, and it's a speed of 50 kilometers an hour. That's a 0x component and a plus 50 y component. I'm going to move this over to the other side because we want to head east anyway. So let's do that. The challenge now is this is our zero vector for velocity. We're being pushed north by the wind. Our goal is to head to tail that vector with another vector whose only property that we know immediately is that it has a magnitude of 800 kilometers per hour, just like the wind has a magnitude of 50 kilometers per hour. And the outcome we're aiming for is in fact a little bit off from what I just showed there. We want to end up going due east. So by the time we add these two vectors together, we end up with a net zero y component. So here what we have is the magnitude of P equals 800, but what we're looking for is either this angle here, or we can actually grab this and move it away for a moment. We can also find that same angle in the opposite part of the triangle there in the upper corner. This angle would represent how far south we would have to aim. So imagine this plane going in a direction. If it was going due east, we would end up being pushed north by the wind. So we're going to have to aim a bit south, not far, but just a bit south, to end up canceling out the component from the wind, the vertical component from the wind. And the challenge then is to track down that angle. Well, the nice thing about this scenario, we can draw it a little more cleanly now that we have the pieces. We know that this side is 50. We know that this side is length 800. And we're looking for this angle. Well, now we're going back to trig. What we know is that this is the opposite over hypotenuse. We know that sine theta is 50 over 800. And so we can solve for theta here. Using our calculator, we get 0.0625 if we are in radians. This will be, however, one of the rare moments where we might want to use degrees. No one's going to say, I'm going to fly my plane 0.0625 radians south of north. And there's no calculus involved here so far. There's no derivatives. So that's usually why we need to use radians, is when we're taking derivatives. If we convert that to degrees, it turns out to be a nice, fairly small angle, as befits the sketch that we drew here. So what we would say is the plane should be directed. And let's be a bit clear about the process here. It should be going east, but we want to angle a little bit south. So 3.28 degrees. The phrasing here is south of due east. The thing that comes last is the element that we would usually be taking. So that's the main ingredient. I'm going east, but I want to nudge that by just a hair. I want to go a little bit south of that direction. And if we do that, the net component will be moving up by 50 kilometers an hour by the wind. And by putting this little bit of angle, we're going to end up going south at 50 kilometers an hour relative to the air in the plane. And we're going to have our net value here of the plane plus the wind altogether being due east, which is the goal in this question. This problem is an excellent reminder of how earlier skills that we had in the course can come back in maybe unexpected ways. Here are the trig functions. You will also see practice problems like this as you go through the notes. So do take a look at those and remind yourselves of the fundamental skills if you find they're a little bit rusty.